So what we are doing today, we're just going to continue.
Things are getting serious now.
What?
I said things are getting serious now.
What do you mean serious?
This is where I start to panic and like get confused.
Oh, this.
Mm.
Oh, okay. It's funny that you say to me now. This is where things are getting serious. Okay, so um, so this is not gonna be long, right? This is not gonna
Mm.
be long since uh also this is this first 2.1 section is not that long, but I would want us only to focus it on today so that we can do a little bit, have the ground, build the grounds, then lay on it, lay
Mm.
on it, then we can go a bit more faster paced. Uh,
Mm.
yeah, so also maybe if we have more time, maybe we could do a couple of questions like
Mm.
for the previous sections that we have done. Uh, like I saw in the book, it said there was a review section where it was combining different types of all the questions from 1.1 to 1.5. So maybe if we have time, we could do that. But yeah, most probably we would have time. Okay.
Before you
Yes.
start, I forgot to ask yesterday, will you give me homework on the sequences and summations since it's not in my book, in the textbook?
Okay. Yes. I will do that. Actually, I was planning to give you for this what you call for this coming weekend. So that on.
Okay.
Yes. So I will do that. Okay. Any other question?
No.
Okay. So we are starting 2.1, right? And it says the tangent and the velocity problems. Okay. Does this ring any bell when we talk of the tangent and velocity problem? Does it ring any bell?
Yes.
Okay. What 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 comes to mind when we talk of this?
Mm, the first lesson that you ever gave me, you told me that the tangent problem tells us how fast something is going.
Mm,
Like it's once you figure that out.
okay. Cool. Which is which is kind of the same thing as so tangent and I think and velocity is kind of similar. So because velocity means how fast something is going, so it's kind of the same thing. Okay.
And that is part of differential calculus.
Yes, it's part of differential calculus. So yeah, yeah, you do remember. You do remember. Okay, so let's see what we have. So gonna start with the tangent problem. So the word tangent is derived from the Latin word tangens, which means touching, right? So I think we have done this in metric, whereby we had like in this diagram here a circle, right? And then we were asked, we were told that line L is a tangent to the circle at point A, right? And that's how they would rephrase that. What you call that's the way that how they would phrase that tangent, you know. So they would say something like that. So
Mhm.
we can think of a tangent to a curve as a line that touches the curve and follows the same direction as the curve at the point of contact. For a circle, we could simply follow Euclid and say that a tangent is a line L that intersects the circle once and only once. So meaning that we're not just touching, but we are intersecting as well. And if it's not a tangent, that means it will either intersect twice or it won't intersect at all. So those are the two things that you should keep in mind. If it's not a tangent, that means it either intersect twice or it doesn't intersect at all. So as in figure 1a, so it touches once, intersects once. For more complicated curves, this definition is inadequate. For example, fig 1b, you can see. So we have this graph, right? We have this graph, but you can see that this is a tangent, but it doesn't follow our previous statement, whereby it only has to intersect once and only once, right? It doesn't, because we can see that it intersects twice, but we are calling it a tangent. So yeah, we have to understand what term can we use. So figure 1b shows a line L that appears to be a tangent to the curve C at point P, but it intersects C twice. So to be specific, let's look at the problem of trying to find a tangent line L to the parabola y is equal to x squared in the following example. So we have to do example 1. Then what does example 1 tell us to do? It's saying find an equation of the tangent line to the parabola y is equal to x squared at the point 1, 1. The equation of the tangent line to the parabola y is equal to x squared. Do you have any idea?
We have points.
Yes,
Mhm.
we have.
Oh, we can use the equation of a gradient to find out what M has.
So what is the equation?
It's MPQ.
MPQ.
Because we need another point. Is equals to y2 minus y1 over x2 minus y1.
Y2 minus Y1 over X2 minus X1. Okay, I have a question here, right? It's so this statement, I understand what you're trying to do, but I have only one part where it's kind of not right with me, is that you're using these numbers, but also this side you're using P and Q. Why I'm saying that, I'm now thinking you're saying the gradient from point P to point Q. So now I'm thinking if maybe we would write it like, yp minus yq, xp minus xq. I'm not sure.
Well, then M of P.
Okay, let's just leave it like that. I think it's something minor. I don't think uh it has is critical. Okay, so what do we do next?
Next, we've already been given 2 points. We can say 1 minus y1 over 1 minus x1.
Mm.
And now we need to find other points to work with. Excuse me. Mm, I'm not quite sure how we get the other points.
Okay, the other points are not numerical. That means they are not numbers, but they can be variables or
Oh,
letters.
One, x1. Y1 can become x squared or x1 squared.
Let's use x squared.
Oh, okay, x squared.
And then x1 will be
X.
x. Okay. So it says find an equation of the tangent line to the parabola y is equals to x squared at the point 1. Yes, at point 1, 1. Do you think this is our answer?
Mm-mm.
Okay.
No.
Let's see what we got. Okay, so it says so we will be able to find an equation of the line as soon as we know its slope. The difficulty is that we only know one point P, whereas we need 2 points to compute the slope. But we observe that we can compute an approximate M by choosing a nearby point x squared on the parabola, as in figure 2, computing the slope MPQ of the second line, PQ a second line from the Latin word seconds, mean in cutting, is a line that cuts or intersects a curve more than once. So we can see this
Mm-hmm.
okay, I think these are just explaining so as okay. Okay. So I think we got our answer here. Okay, any question?
No.
No question. Okay. What's next? So Fig 3 illustrates the limiting process that occurs in example 1. As Q approaches P along the parabola, the corresponding second lines rotate about P and approaching the tangent line. So we are talking about L is the tangent line, right? L is the tangent line and Q is the second line. So which is the blue one. I'm not sure if you can see. Can you see?
Yes.
Okay. So now at the top it's showing where the second line is approaching the tangent. So it's going more to the right. Here it's going more to the right. Here's going more to the right. Here it's going more to the left. Going more to the left. More to the left. Okay.
Mm.
Okay. So let's now do example 2. Okay. It says a pulse laser operates by storing charge on a capacitor and releasing it suddenly when the laser is fired. The data in the table describes the charge Q remaining on the capacitor, measured in coulombs, at time t, measured in seconds after the laser is fired. Use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t is equals to 0.04. Note the slope of the tangent line represents the electric current flowing from the capacitor. Okay, so we have a table and we are told use the data to draw the graph of this function and estimate the slope of the tangent line at the point. Okay, so we have 0, 0.2, 0.02, 0.04, 0.06, 0.08, 0.1. Then is 10, 8, so on. Okay, so what scale should we use for the y, for the vertical?
The Y is T.
Yeah, it's 10, yeah, but what should we use? 2, 4, 6, 8, 10? Or yeah,
Yeah, 2, 4, 6, 18.
0, 2, 4, 6, 8, 10. Okay, and What about the x? What scale should we use?
For time, the same, I guess. But it, excuse me, the same, but in decimals, like 0.02, 0.04.
0.02, 0.04, 0.06, 0.08, 0.1. Okay, so 0 to 10. Let's use red. I'm going to mark here. 0.2 to 8.187. 0.4 to 6.7. 6.7. Somewhere here, I think. 0.6, 5.488. 0.808, 4.4. Zero point 0.1 and 3.6. Okay. This okay. So we have this, but I want us to maybe do it more accurately. Do it more accurate. So settings, show grid. Okay, so 0 to 0.1. And we have 10 to 0. 0 to 10. Okay, I wanted us to do it a bit more accurately, because from what we call, from the question, like from the number of decimal places that they have, it's quite accurate. So let's try it and see if it makes sense. So what's the first one? 0 and 10. So 0, 10. And come here. So 0, 10. Okay. 0, 10. What's the next one? 0.2 and 8,187. Okay. 0.2. Where's 0.2? 0.2 is here. Let's try and zoom. Let's see. 0.2. 8, we said 8, what?
It's
187.
187.
8.8, 8.8, 8.6, 8.4, 8.2, 8.1 will be in the middle, and 117 should be somewhere here. Where's 0.2? 0.2 is there. So 0.2. Somewhere here. Make it big. Okay. What's the next one? 0.4 with 6,703. 6, 0.4 and 6, 6,7. 6,7. Okay. What's next? 0.6, 0.6 and 5,480.
48.
0.6, 5, 4, 5,4 here with 5,5. So it should be here. We have now 0.8 and 4,49. 4,49.
9.
So last one, 0.1 and 3,67. 6 or 67. These kids nowadays.
I still don't understand what it means.
It has no meaning. It has no meaning.
Mm-mm.
I saw a video where it was trying to explain where it came from. It came from one of these American rappers who sang it in his song, and that guy is like super like dark side, spiritualistic. So they said that he even makes others. He makes like songs that uses like those names for different type of gods.
Mm.
So yeah, I saw some people were saying, yeah, it's kind of demonic. They said this to a greater extent. But yo, these kids are crazy over it.
Mm.
Yeah. Just pray for them that they will get, that they won't be hooked forever. What did we say? We said 3,676. 3,6 will be 6,5. 7 should be here. Submit there. Okay. Does this look straight or does it look curved?
Ish.
Yes, it kind of looks curvish. Okay. What was the question again? It said, okay, use the data to draw the graph of this function, estimates the slope of the tangent line at the point where t is equals to 0, 0,04. Okay, so okay, 0,04, where are you? You're there. Oh, I didn't join with the last. That's weird. Okay, so it said 0,04. Okay, what do you think we should do to find the gradient?
We can use the gradient of this line. We can use the points at 0 point. Excuse me. And can we use that one with 10? 10 and 0.
Okay, 10 and 0.
Yeah, just because they don't have lots of decimals. We can say 10 minus, this is what the next point here.
You mean this point, 0
Yeah.
0.02?
Yes.
It's 8,187.
We can say 10 minus 8.187 divided by 0 minus 0.02.
But we are looking for where t is equals to 0,0.
Oh, sorry, I didn't realize. Then we can say 10 minus 6.723 over 0 minus 0.04.
Okay, say that one more time.
10 minus 6.703 divided by 0 minus 0.07.
So we say 10 and 0 and 0.74. 6.70 is equal to 3,297 over negative 0.04. 297. Okay, so we get 329.7 divided by 4. 8.92 from to 17.4 to 2 5. I think that's what we got.
What happened to the negative?
Or the negative, sorry. That's what you, okay, but the only thing is that the only problem with your idea is that it's no longer a tangent. Why do I say that?
It goes through
Because it goes
time.
yeah. So it will be cutting from here straight to there. Is there any other method?
We have to estimate the slope.
Okay. How do we do that?
We can, on the map, we can just look for a point that's slightly above the the graph so that it doesn't touch.
So that it doesn't touch.
Mm.
Wow.
We can draw a tangent line and then find the point.
Okay, let's try that. Tangent line. Hmm. Hmm. Maybe I'll use points. Draw it. Oh yeah, use this. Let's look from afar. Is this look like a tangent line?
Yeah, looks like it's trying.
It's trying. Yeah, the diagram is so bad. It's trying its best. Okay, so maybe if we, yeah, maybe if we use this. Okay, okay. So let's try and check uh this point. What is this point? Looks like 2,0206 and 8. So maybe if we say 8 minus 6,703 over 0,0206 minus 0,04, we get what? So 3,297, 1,297. 0,04, 3,9,1,0,0. So negative 0,094. One, two, three, four. 10,000. Okay, so I think let me now involve a calculator because this looks too big. We say 1,297 times 297 times 10,000 divided by negative 100. Got negative 66, 855. From, okay, from negative 82,425, negative 66,855. Okay, let's now check what our answer could be. So the plot and it looks curved. So given the points 0, 0 and 10, we find that the slope of the second line PR is, and the table at the left shows the results of similar calculations for the slopes of the others. From this table, we would expect the slope of the tangent line at t is equal to 0,104 to lie somewhere between minus 74.20 and minus 60.70. In fact, the average of the slopes of the two closest second lines is equal to negative 67,475. So this method, we estimate the slope of the tangent line to be negative 67.5. Okay, so what they did is that, right, is that they used the method that you used, right, the first one, but they did it for all of the other points that we had, all of the other points besides the 0,041. So here's 0.10, 0.002, 8,187, and then they found the gradient for all of those and then averaged, right? Which will give them an approximate answer, which is kind of their method, right? And then, which is what they say, one of the methods. So that's how they estimate it. So another method is to draw an approximation to the tangent line at P and measure the sides of the triangle ABC. Okay. And then this gives an estimate of the slope of the tangent line. So now the other method, I'm not sure if this is this different from, let's see if this is different. I want us to try it out and check. Maybe it's, so what they're saying, right, is that they made a tangent line, right? Tangent line like this. Then they have another line, should be straight. Should be a straight. Straight. And then another line. Okay. So they're saying that we have we first had our tangent, right? And then now we draw a vertical line, then we draw a horizontal line, forming a triangle, right? Forming a right angle triangle. So they're saying that we can measure well the sides of the triangle, and then we can use what you call, we can use y over x, right? Y, like the y interval over the x interval. So let's try that. So G, what's point G? Point G, x is 0, comma, x is 0, comma, 0, 3, 3. And then here 0, 3, 3, so 0, 0.05, 0, 7, 0, 0.0507. So this is for x, y. What does it show us? We have 6, 0.0639, 395, 0, 6, 0.06, 6, 0.06935, and we also have 7,1808. 7,1808. Okay, so let's try and work this out. So you might be asking, I didn't put these guys in order.
Mm.
I didn't put these guys in order. So with such a method whereby you're using the triangles, right? Whereby you're using the triangles, it doesn't really matter of which one comes first or which one comes second. Why do I say that? It's because you're just going to take you're just going to use the, what you call,
Mm.
oh no, I think, yeah, it does. Why was I thinking that? Okay. Okay, so here we're going to just type 0,0507 minus, I'm just going to do the opposite, 0.33. What do we get? 0,0177. And then the other one, 7,1808 minus 6,06935, get 1,11145. Okay, so since So since the gradient, we always have y on top and then x at the bottom. So we take the y 1, 1, 1, 1, 4, 5 over 0, 0, 1, 7, 7. Let me write this, guys. Then let's see what our answer will give us. Hmm. 65, comma 379. And then it's negative because it's decreasing. Okay, so this is the method that they used, right? For the second one. And then they got negative 65. Listen, we got negative 65,399, which is very, very close. So that's the method that they used instead of trying to get a point from here, then a point from there. But it should generally give us this. I think this is the same. This should be the same. This is the same way as the method that we used at first. The one that we got, I mean, this at the second method where we got negative 66,855, right? It is the same method, but it's just that our points are a bit different. That's why it came out a bit different. Because this is a triangle. So our tangent is like this, and we are taking a point from here and here, right? But if this is the same tangent, and then we use this method whereby we go from here, then we go here, the gradient should generally be the same. Maybe it's because of the points. There's been a slight difference in points. But do you have any question?
No.
No. Okay. So you saw the two methods that they used. The two methods that they used. So the first method, they found the gradient of each other of the other points, then averaged them. But for something a bit more precise, they would use this, and that's where we got negative 65,0. Our answer at first, we got negative 666, which is pretty decent and very close. Any question?
No, I don't have a question.
Okay. So now we're going to velocity problem. So if you watch a speedometer of a car as you drive in city traffic, you see that the speed doesn't stay the same for very long. That is, the velocity of the car is not constant. We assume from watching the speedometer that the car has a definite velocity at each moment, but how is that instantaneous velocity defined? Let's consider the velocity problem. Find the instantaneous velocity of an object moving along a straight path at a specific time. If the position of the object at any time is known, in the next example, we investigate the velocity of a falling ball through experiments carried out for 4 centuries ago. Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. This model for free fall neglects air resistance if the distance fallen after t seconds is denoted by s of t and measured in meters, then at the Earth's surface, Galileo observation is expressed by the equation S of t is equal to 4.9 t squared. Okay, so before we go further, right? So this is an equation that a scientist named Galileo from back in the day used to, or formed from doing many experiments of a freely falling body, or free fall, where we call that free fall. You just take a ball or something and then just let it go without applying any force, just like how we do, like when we throw someone a ball, we actually apply force, or when we are trying to push something down, we're actually applying force, but when we just let it go, it starts falling on its own. So this is derived from those experiments, and it says it's looking for distance, right? Distance. Actually, it's looking for what the letter S in physics, right? In physics, it is used as displacement, not necessarily distance. But it can be the same thing. Do you know the difference between the two, displacement and distance?
Sorry?
I was asking a question. Have you heard of a term called displacement?
Mm, I know what displacement means, but I don't know if it's different from the mathematical term of displacement.
The one that you know is from where?
Like it's just being displaced, like English.
Or in English?
Yes.
No, there's another one that is used uh, in physics that makes sense with the English one, but it will be hard to get the physics one from the English one, I would say. But once I explain it, you can see like it kind of makes sense, kind of relates. So let me go here so that I can have. So when we talk of distance, right? Distance is traveling from one point to another, right? So AB, right? So that's what we call distance when we travel from one point to another along a certain route, right? Along a certain route. So a distance can be like this. So from there to there, we would say it's 50 kilometers, but from A to B, the distance we call it 50 kilometers. But there's a special word that they now introduce, which they call displacement, right? Displacement now is a bit different from distance because displacement now involves the distance from 2 points, but in a straight line. Right? So so now so displacement is actually like the distance of 2 points but in a straight line. So that's why it's a kind of a bit different from distance, because distance is not defined, it's not restricted to for it to be straight. If it's turning around, then it goes Then if it goes all the way back, that's the whole distance, right? That's the whole distance of the journey. So it doesn't, or in certain scenarios, right? Or in certain scenarios, if you're coming from A to B, you would go like this, and then you think, oh, I messed up. I used the wrong route. Then you go back, then you go back, and then you find the other route. Then you go like here. Then you go to B. So we would calculate all of that with distance. But now displacement is just in a straight line. So in physics, when we were doing physics, displacement is denoted by the letter S, and then distance would be denoted, I think, by the small letter D. So now, when we go back here, now when I see the letter S, I think of displacement, of which it's even though they say distance, right? But it's, even if they use distance in this scenario, it's actually true, because when we are dropping from a building, or just dropping an object in general, it's just going to go straight. It's not going to turn because we are neglecting air resistance, so it's just going to fall straight. Does that make sense?
Yes.
Okay. So also clarifying that it's just straight because we have no air resistance. So air resistance is the thing that could make us turn a bit before we go before we reach the ground. Okay, so you can see it says S of t is equal to 4,9 t squared. Okay, let's see. We have to do example 3. Okay, what does example 3 say? Suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Velocity of the ball after 5 seconds.
Hmm.
Sure.
Hmm.
Yes, 4.9.
Hmm.
Okay. Okay, I'll let you think a bit.
Where's that? Ooh. Mhm.
Mm.
Hmm. Is it 4.9 times 5 squared?
Okay. 4.9 times 5 squared. No, it's not. Okay. So first, right? First, what is this representing?
S of t, that is the distance?
That's the distance. Okay. So now when you're saying 4,9 times 5 squared, now you're saying that's the distance of which we are looking for the velocity.
Mm-hmm. To be 450 over 450 divided by 450 divided by 5.
450 divided by 5.
Yes,
Okay.
because speed is what's distance divided by time.
5. Okay. Maybe okay. Maybe let's do this. So maybe I could ask a question. So when you put in 5 as when you are placing t with 5, what were you trying to do?
When I was doing what with what? The
You
first
were
time
yes, the
when
first time.
when I was replacing T with 5, I don't know why I was doing that. I'm joking. I was trying to figure out
The distance.
the distance, yeah.
Okay, the distance. Okay, let's try that. Maybe it will work. Let's try. S of 5, 4,9 times 5 squared, 4,9 times 25. What do we get? Look at me doing things a lazy way. Oh, 125.
Mm,
Did you see what I did?
way.
From here to here.
25 is 100 divided by 4 is 25.
Then I said 4,9 times 100. Then I got 490. Then divided by 4. So it's like it's funny because you're going back here. You're going backwards because you're simplifying. You're actually taking 25 and then saying it 100 over 4, which helps sometimes. So we got 125. Is it 125? No, it shouldn't be 125.
It's not.
It's not. It's what?
22.5.
2.5. Okay, 122.5. Okay, we've got 122.5. That's the distance that we traveled in the first uh, 5 seconds. Okay, do you want another clue? Hello? 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 Ledwina, I can't hear you. Hello?
Hello.
Hello?
Sorry about that, Shim. Sometimes we have bad days with our Wi-Fi.
Oh, fine. Okay. So, uh, so we might, is there any way we could use maybe what we learned from the tangent problem that could be possibility that we could use?
Can you please rephrase the question? Are you asking like how we can apply what we learned from the tangent problem section? Yeah.
Yes. Is yes.
Um, we can use not the distance formula per se, but yeah, distance, the gradient formula, like the speed. I mean, 450 minus 122.5 over 0 minus 5.
Okay, so you said 450
Mm-hmm.
minus what?
Minus 120.5. 122.5
122.5 over
over 0 minus 5.
0 minus 5. Okay. So 450 minus 120. 10 minus 5, 5, 10, 3, 7, 3, 2, 3. 3, 327.5 over negative 5, 6, carry 2, 5, carry 2, 5. So negative 65.5. Okay, this would be
Wrong.
no, that's not the word I wanted to use. This would be, I was saying this would be distance over time. Okay, distance over time, which give us velocity. So it makes sense.
So am I right?
Not, not really. But I like that you used. I like that you used. You got the idea. Okay, so the the mindset is correct, right? But the numbers are not all the numbers are necessarily correct. Why am I saying that? It's because there's a statement that says find the velocity of the ball after 5 seconds. So now with that mindset now, and with the part that's specified after 5 seconds, how would we work it out?
I'm not showing. Yeah.
Okay. So, okay. So, meaning that we have to, so isn't you found for 5, right? You found for 5. We have to find for, we have to find for a number that is very, very close to 5, but after 5. So, meaning that we can use 5,1. So we would write S of 5,1 is equals to 4,9 times 5,1 squared. So 5,1 squared times 4,9, what do we get? 127,449. So now, meaning that we are going to say 127,449 minus 122,5 over 5,1 minus 5, right? And then at the top, we subtract, we get 4,4, says what? Oh, 4,949 over 0,1, then it will become 49,49. Okay, so this would be our answer. Okay, do you know why we use 5,1?
Because it's just after 5.
Yes, because it's just after 5, and we don't want a gap. We don't want a gap that is large, right? Because we don't want a gap which is large, like 5,5, because
Because then it could become a secant.
yes, it could change. It could, what you call, we could get further and further from what you call, the, is the you get further from the correct gradient, because now it won't follow the same principles that we had when we were doing here. Isn't we used 10, right? We used 10, which is far away, which didn't work in that situation. We needed something that is very close uh, for us to get a value that is that tells us the velocity after when the ball is after 5 seconds. So it says after, so 5,1 is the simplest number that you can use after 5. Any question?
No.
No question. Okay.
No.
Okay, cool. So let's see. Okay, so it said the difficulty in finding the instantaneous velocity at 5 seconds is that they are dealing with a single instant of time, so no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of a tenth of a second. Okay, so does this make more sense?
Yes, it does.
Okay, so average velocity is equals to change in position over time elapsed. Then we said s of 5, 1 minus s of 5 over 0, 1. Then we get 449.49. The following table shows the result of similar calculations over the average velocity over successful smaller time intervals. So this was the time interval from a tenth after a 5th second, right? And then here it's between 5 and 5,05. Here it's between 5 and 5,01. Then here 5 and 5,001. And you can see that it's becoming more and more precise, right, as we reduce the time interval between.
Mhm.
So yeah, so let's just go check. So yeah, so since we are talking about instantaneous velocity, we want something that is very, very close, very, very close, which is a tenth. Mostly. Do you have any questions?
No, I don't.
Okay, cool. You don't have any questions. So it says it appears that as we shorten the time period, the average velocity is becoming closer to 49 meters per second. The instantaneous velocity when t is equal to 5 is defined by to be the limiting value of these average velocities.
Sorry, can I just answer this quickly?
Okay.
No. Okay. I'll call you back on the we should begin. Bye. Okay, I'm done.
Okay. So so saying the instantaneous velocity when t is equals to 5 is defined to be the limiting value of these average velocities over shorter and shorter time periods that start at t is equals to 5. Thus, it appears that the instantaneous velocity after 5 seconds is 49 meters per second. Okay. You may have the feeling that the calculations used in solving this problem are very similar to those used earlier in this section to find tangents. So you can see the similarities between when we were doing the tangent problem and the velocity problem. You can see we were using kind of the same logic. In fact, there is a close connection between the tangent problem and velocity problem. If we draw the graph of the distance function of the ball as in fig 6, that one, and we consider the points 5 and 4.9 times 5 squared, and q, which is 5 plus 8 and 4.9 times 5 plus 8 squared on the graph, then the slope of the second line, PQ, is 4.9 plus times 5 plus 8 squared minus 4.9 times 5 squared over 5 plus 8 minus 5, which is the same as the average velocity of the time interval 5 and 5 plus 8. Therefore, the velocity at time t, the velocity at time t is equal to 5. The limit of these average velocities as h approaches 0 must be equal to the slope at slope of the tangent line at p, the limit of the slopes of the second line. So what they're trying to say is that when h, you can see there's an h, when h approaches 0, the whole the gradient of the tangent line, or the gradient, will be closer and closer to this, which is the tangent line P, will become closer and closer to P. Example 1 and 3 shows that in order to solve tangent and velocity problems, we must be able to find limits. So when they talk about limits, they talk about do you understand what they mean when they talk about limits?
When they talk about
Limits.
limits. Yes, I understand it. It just, yeah.
Okay. Are you able to describe it?
I can try to put in my best word.
Okay.
Like a limit is when a function is like approaching a value, but I don't think it ever touches it. Like it always gets closer and closer, but it's called a limit because it doesn't get to it.
Okay. So you're saying it's like an asymptote.
Yeah, I would say so. Well, yeah, I would say so because I don't know if it's like, I'm not saying it's the whole function. I'm saying it's a point in a function. So I don't know if that changes things because if it's the whole function, then yes, it would be an asymptote. But if it's a specific point in the function, I don't know if it's still necessarily, you know, an asymptote. Yeah.
But yeah, I think you do have the gist of the story, where especially the part where you say approaching a certain value. We are approaching a certain value, which in this case we are talking about P being the limit. So the P, tangent line P, is the limit. So so that means the second line is trying its best to get closer and closer to P, which is just what you just said. So I think you you do have the idea. Yeah, after studying methods for computing limits, in the next 5 sections, we will return to the problems of finding tangents and velocities. Okay, so we ended there. Do you have any question?
No,
No question. Are you sure?
100%.
Okay, cool. Let's see. Okay, let me answer this call. Hello.
Hello?
Good. How are you? No, not at the moment. I yeah, I don't think we'll be able to get them for Sunday. Sorry, sorry. We have the washes. We don't have the lotions. We have quite a lot. I haven't checked, but mm, yes. For 12, it was 108. Okay, it's okay. So, sorry about that. Sorry.
That's okay. I was confused a little bit at first. I thought it was my WhatsApp web ringing.
Oh no, it was mine.
Mm, I realized I'm like, no, I don't know that number.
Try number 22.
Oh, like right now.
Like right now,
Okay.
on the spot.
Give me a second. I had packed away my stuff when you said we were in here.
Oh, sorry. Sorry.
Eh, Okay. My final answer is f of small f of x is equal to the square root of x. G of x is equal to x squared plus x, and then h of x is equal to 1 over the square root of x. And then it's the composite was f into g into h.
Okay, so you said what again?
Can I start again?
Yes. You said f of x is equals to square root of x.
Yes. G of
G
x is equal to x squared plus x.
squared plus x. Okay.
And then h of x is equals to 1 over the square root of x. And when you write the equation, is the capital F of x is equals to h, that circle,
Or h.
g, that circle, small f, that circle, like the composition circle, and then bracket of x, um, or the other way.
Did you say HGF?
Yes.
Okay. Okay. So let's see. F of x, square root of x. And g of x squared. So it will give us x plus square root of x. Then it gives us 1 over. Okay. Nice, nice, nice. Nice. Let's see if there's any other interesting. Um, 7. Number 7.
Yeah. Mhm. Mhm. Right. Okay, yeah. So the range of x is an element of real numbers. Kiwi.
You said in interval notation.
Oh, an interval. Ish, I need to learn the difference. Which one is interval? One with brackets.
Yes.
Interval notation. Also, an interval notation is. You still write y is an element of no, and then I see brackets, negative infinity to positive infinity.
No, that would be set builder notation.
Oh, so the range is just negative infinity
So
to positive.
you just write range, then you write using the brackets.
Oh, so the range is brackets negative infinity to positive infinity.
What are the type of brackets?
Rounded one.
Okay. And domain?
The domain is domain brackets -6 to positive infinity.
What type of brackets?
Round.
Both of them.
Yes.
Okay. Cool. Nice. Don't think I will ask any more questions. Yeah, since you have to prepare for your next lesson.
Okay.
But yeah, when you have time, you should check these questions out.
Okay. Thank you.
It's okay. See you next week. Are we on
Right.
next week
Yes.
or
Yeah.
Monday or Saturday?
Oh, I'm available tomorrow. I don't have anything. I'll be at home.
Are we available tomorrow?
Yes.
I won't be available tomorrow.
No, that's okay.
So we see you on Wednesday.
Yes.
Okay, cool. See you.
Okay, bye.